In the next part that we are going to discuss is the Stefan's law. Stefan's law for black bodies. In the Stefan's law, it says the total radiation energy E emitted per unit time per unit area of a black body is proportional to the fourth power of its absolute temperature. So here E means that is the total energy emitted per unit time per unit area of a black body. So this is different from E lambda that we have discussed in the previous session. E lambda, the difference between E lambda and E is this intensity, which is there in the Stefan's law, has mentioned the total energy per unit area per unit time. But E lambda in the previous session, that is known as radiation intensity. It has mentioned about a unit wavelength. For a particular wavelength, what is the total energy emitted per unit area per unit time for a particular unit wavelength. But in the Stefan's law, it has mentioned not for a particular wavelength, but for all the wavelengths. There in the spectrum. So this E means the total energy emitted per unit area per unit time by all the wavelengths emitted by a body, that is directly proportional to fourth power of absolute temperature. So T is the absolute temperature there. Then by combining that relationship, so you know this is only directly proportionate. To make it equal, we have to put a proportionality constant. So that is sigma. We call it as the Stefan's constant. The value is given here. So we can write down the equation as E equals sigma T to the power 4. So we can apply this equation to find the total radiation energy emitted by a certain hot object. Then if you want to find the power, power means energy emitted per unit time. Then to find the power, you have to multiply sigma T to the power 4 also by A, the surface area. A is the surface area. So the difference between this E and this P, this E is the total energy emitted per unit time per unit area. So this is E for the energy emitted per 1 square meter area and also per 1 second. This P means that is the energy emitted per 1 second only, not for 1 square meter area, but from the entire surface. This is the equation for non-black bodies. The previous two equations are only for black bodies. So if you want to find the energy emitted by a non-black body, then you have to go by this equation. Here is this is also energy emitted, the total radiation energy emitted per unit area per unit time is equal to E. E is emissivity. You have to put the value of emissivity here because for black bodies E is 1. Therefore, you don't put 1 there. That's why you get this equation. But for non-black bodies, it's less than 1. Therefore, that value should be additive. So E is equal to simply emissivity, sigma Stefan's constant, and T to the power 4. T is the absolute temperature. Then we are going to discuss about the intensity distribution curve for black bodies. Intensity distribution curve for black bodies. That is the graph between intensity on y-axis and wavelength on x-axis. For a black body, all these graphs have been plotted only for black bodies. So this is why intensity is actually E lambda value, radiation intensity for particular wavelengths. What is the total energy emitted per unit time, per unit area? And on this side we get wavelength. For example, if you take a black body and it will emit radiation, when the temperature of the black body increases, the amount of radiation emitted by it is also increasing. So in this, the idea of this graph is now for different temperatures. You can see for 3000 Kelvin, for 3000, 5000, this graph shows the amount of radiation emitted by a black body at these different temperatures. So for example, if you take this curve is drawn for a black body at the temperature 4000 Kelvin. If you take this point, there the wavelength lambda is 0.5 micrometers and the corresponding intensity is 1 watt per square meter. The idea here is, if you take a certain black body which is at temperature 4000 Kelvin, it will emit radiation. All the radiation will be emitted there. You select a particular wavelength out of it, that is 0.5 micrometer wavelength. From that wavelength, what is the total amount of energy emitted per 1 square meter area per 1 second? That is, according to the graph, that is 1 watt per square meter. So that's the idea of this graph. You select a particular wavelength. From that particular wavelength, what is the total energy emitted from this black body, a 1 square meter area of this black body per 1 second. So like that, for different wavelengths, you get different values. And also, with the increase in temperature, you can see the intensity has also gone up. The curves has gone up like this. So first one is said, each curve gives the intensities. Intensity means here the radiation per unit area per unit time. Each curve gives the intensities of different wavelengths for a given temperature of a black body. So these are only for black bodies. Second one, as the temperature rises, the intensity of every wavelength increases dramatically. That proves the Stefan's law. So what does Stefan's law say? This intensity is proportional to fourth power of absolute temperature. So with the small increase in temperature, will dramatically increase the energy released by the black body. Third one, the intensities of shorter wavelengths and longer wavelengths are low for a given temperature. So you can see all those temperatures, the shorter wavelengths and the longer wavelengths, their intensities are much smaller than in between this region. Here you can see in this graph, with the increase in temperature, the maximum intensity, the wavelength of maximum intensity is shifting towards the lower wavelength side. Lambda max. Lambda max is the intensity of lambda max is the wavelength of maximum intensity, which means now, as I mentioned earlier, a black body is emitting all the wavelengths, but not in equal amounts. Some wavelengths are much higher. The amount of some wavelengths are much higher than the others. So this lambda max is the wavelength which is emitted mostly by this object. So that is lambda max. So in this graph you can see with the increase in temperature that lambda max, the wavelength of maximum intensity, is shifting towards lower wavelength side. When wavelength decreases, the frequency is increasing. So you can see here for 3000 Kelvin, lambda max is there here, which is in around 1.2 micrometer range. But at 4000, that is around 0.9 micrometer range. When the wavelength decreases like that, frequency and the energy is increasing. So this is the infrared part, infrared region. And it is shifting towards the visible region. When it comes to 5000 Kelvin, the maximum wavelength is there in the visible region. The wavelength decreases up to visible region. Then at 6000 Kelvin, you can see that lambda max is there completely inside the visible region. So 6000 is the temperature of sun. That's why the sun is emitting more visible light than the other light. So even in this graph, you can see that lambda max is shifting towards the shorter wavelengths. So the relationship, we can write it as lambda max is inversely proportional to temperature, which means with the increase in temperature, the wavelength of maximum intensity decreases. And here it says the intensity distribution of wavelengths emitted by sun is the same as that of black body at about 6000 Kelvin. The temperature of sun surface is about 6000. Some stars are much hotter than the sun and appears blue. Because if you take the visible spectrum, so this is high wavelength, this is smaller wavelength. What it says, when the temperature increases, wavelength decrease. So sun's temperature comparatively, if you take the sun's temperature and if you take another star which is having a larger temperature than sun, so with the increase in temperature, when the temperature increases, the lambda max decreases and it is shifting towards high frequency side. So sun is emitting yellow color, and if you take another star which is much hotter than sun, so if the temperature has gone up, then lambda max decreases and it should shift towards high frequency side. So this is high frequency. Blue is, the frequency of blue is higher than the frequency of yellow. Because that star is much hotter than sun, the maximum intensity, the wavelength of maximum intensity has shifted towards the blue color side. Then the next part say the black body radiation has the highest intensity because surface emissivity is 1. All the other objects are having surface emissivity less than 1. For any objects, A is equal to E. The next one, energy radiated per square meter per second over all the wavelengths is proportional to the area under the curve. So if you take the intensity distribution curve again, if you take the curve for a particular temperature, this area under the curve gives the total radiation energy emitted by all the wavelengths at that particular temperature T. But if you take a point on this curve, that indicates not the total energy. For this particular wavelength, what is the intensity emitted by the black body? For all these points represent for a particular wavelength what is the intensity emitted by the black body. But area under the curve gives the total radiation energy emitted by that black body for that particular temperature. The next one say, if a body having temperature T1 is placed in a surrounding having T2 temperature, if T1 is greater than T2, the rate of net energy loss as radiation is given by R. So what is R? R is the rate of net energy loss as radiation. Rate of radiation loss. So when a certain object is placed in the environment which is having T1 temperature and then room temperature is T2. So if T1 is greater than T2, more radiation will be emitted. But a small amount of radiation will be absorbed back. So this part is the amount of radiation being emitted, because this E is for the emissivity, emitted. And this part gives the amount of radiation reabsorbed. To find the net amount, you have to subtract the absorbed amount from the emitted amount. And here, if T1 is equal to T2, which means if there is no temperature difference between the room temperature and the object's temperature, if there is no temperature difference, then no net heat loss, no absorption or no loss. So this is the equation we are using to find the velocity of electromagnetic waves or thermal radiation. Then we'll go to the next part, Wien's displacement law. We have already discussed the Wien's displacement law. It says the intensity distribution curve shows that lambda max shift towards smaller wavelength as temperature increases. So we have already discussed that this lambda max, wavelength of maximum intensity, is inverse proportional to absolute temperature, which means when the absolute temperature increases, the wavelength of maximum intensity decreases. With the increase in temperature, lambda max is shifting towards the smaller wavelength side. That is known as Wien's displacement law. So from that, we can derive, from this relationship, we can derive equation subjecting lambda max and T. Then you get this equation, the Wien's law. as lambda max is inversely proportional to absolute temperature, to make it equal, to get an equation, we have to put a constant here. We take it as C. So C over T. When you subject C there, you get lambda max into T is equal to C. So C here is known as Wien's constant. This is C, Wien's constant, and the value is given here. So this part, this side is a constant. As this side is a constant, we can use this equation even for comparing two temperatures, as lambda 1 T1 equals lambda 2 T2. We can compare wavelengths of two different temperatures. So even in this graph you can see those lambda max values are shifting towards shorter wavelengths side with the increase in temperature.